All right, guys. So we're going to start chapter 22, which is on magnetic forces and magnetic fields. So this basically, covers magnetic phenomenons. So we covered electricity or electric phenomenon in chapters 19 and 20. In chapter 21, we looked at application, which is the circuits. And then here we're going to look at magnetic phenomenon. And magnetic phenomenon actually, has been around for a very long time, or people were aware of those for a very long time. So actually, probably even earlier than electrical phenomenon. And obviously, one of the best application of the magnetic phenomenon is a compass, which you can see, right, has been used by China as early as 13th century BC. So that's basically over 4,000 years ago or 3,000 years ago. So, and again, it's been known everywhere, right? So in China, in India, everywhere, including, Greece. And actually the name magnetism, right, comes from Greeks. So there's this city, Magnesia, where Greeks first discovered, that particular phenomena. And, you can see, right? So there's this material called magnetite, obviously now we call it magnetite, right? But they were discovered, these pieces of rocks that can attract iron, all right? And that's why this place was near the Greek city Magnesia, so the name kind of magnetism come from that. And obviously, let's say there was more or less very simple, idea of the magnetism. They were just basically able to see effect, but really not understand much of it until maybe Middle Ages, where we have Pierre de Moricourt, who found that direction of a needle near a spherical natural magnet formed lines that encircled the sphere. Okay, and those lines pass through 2 points diametrically opposed to each other, and he called those poles. Okay, that means he discovered that if you have some kind of magnetic object, well, it has two sides, sort of like one is north, the other one is south, so he called those poles, right? So right now we have north pole and south pole, which is basically similar to the positive and negative charges, like like in an electric dipole. All right, so one of the things that basically he discovered is that you have those you know two type of properties. So like one is north, the other one is south. And through the experiment, you can even see that when you bring two magnets toward each other, there are two sides that can actually attract each other and two sides that can repel each other. So, and very similar to the electric effect, when those two things are the same, right, the same poles, they, attract each other. When you have opposite poles, right, then they, uh, sorry, when they're opposite poles, they attract each other, and where the same poles, they're basically repel each other. So kind of similar to, if you have sort of electric charges, right? Positive attracts negative, and but positive repels another positive, and negative repels another negative. So here you can think of, like, let's say here's a magnet, and let's say if this is the north of one magnet, and let's say here's the south of that magnet, right? If you bring another magnet, and let's say here's another magnet, and this is the north and south, like that, you can see, right, north facing north. So there are like charges, they're going to be repelling. So overall, there's a force that pushes them apart. And the same thing will happen if you bring, here's north south, here's south north. You can see south and south are facing, and they also gonna repel each other. So there's a repulsive force, pushing them apart. Well, obviously, if you bring two that are more or less same configuration, right? That means, this, let's say north south, you know, north south, but south and north are facing each other. then they attract each other. So there's an attractive force between them, and those magnets, move toward each other. Very similar to when, let's say, you have positive charge and negative charge, right? There's an attractive force between them. So this is, we're going to use B, we're going to see for the magnetism, right? B is for magnetic force, right? And Fe for the, let's say, electric force. All right, so we had to wait until about 1600 or so for the most of the properties of magnetism to be discovered. And then we have William Gilbert, who actually discovered that magnetism is not restricted to certain rocks. So technically, um, and that either objects can, more or less, can be considered as magnet or magnetic source. And he was the one who actually suggested that Earth can be basically a large permanent magnet. And, when you were using a compass, right, so that basically discovers, Earth's magnetic fields. Okay. And we have John Mitchell showed magnetic poles exert attractive and repulsive forces on each other. That's kind of what I talked about. I jumped a little bit ahead, but, remember, so this concept of force technically comes from Isaac Newton. So this is about Isaac Newton, a little bit after Isaac Newton, right? So when they started talking about things in terms of forces, okay? But still, what you have here is very similar, right? Attractive, force and repulsive force depends on which poles you are considering, okay? So, and one of the important things that we will consider later in this chapter, just like electric force, that was inversely proportional to the distance squared, right? Same thing, magnetic force will also be inversely proportional to the distance squared. That means further you go from the magnetic source, weaker the force, and it drops as 1 over r squared. So that's why it's also known as an inverse square law, okay? All right, so one very important thing here about electric charges or electric effect compared to magnetic charges and magnetic effect or magnetic phenomena is that, for example, if you have a dipole, electric dipole, which is positive and negative charges, right? So and there's they generate electric field and all that things, right? So kind of like plus Q, this is negative Q. Well, one thing I can do here is I can remove one of the charges and have just one charge. That means I can have an isolated electric charge, positive or negative. So that means I can have, electric monopole, okay? But there is no such thing as a magnetic monopole, okay? So magnetic poles are always found in pairs. And one of the things we can do, for example, if I take a magnet and let's say this is north and this is south, and if I, let's say, cut it in half, and basically the theory is, okay, if I cut it in half, then this guy gonna be south and this guy gonna be just north. Well, not so much. So basically what we get here is this left one, let's say, for example, right? Let me do it here like this, something like this. So this one, so as soon as you cut it, right? So this south stays south, but the other side becomes north. And the second piece, this was north, then that one becomes south. What if you cut it again? Well, same thing. So you have then south, north, north, south. And you can continue cutting like that. You're still gonna get always, pair of, north and south, all right? So that's why there is no such thing as magnetic monopole, okay? It doesn't exist, haven't been experimentally discovered. So that's why no matter how many times you take the permanent magnet and cut it, you're always gonna get magnet with north and south poles. Obviously, there's something you're changing about the property of the magnet. Every time you cut it in half or you break it in half, you're actually making it weaker, okay? So, but still, you can still have a magnet with the north and south poles. All right, so Hans Christian Ørsted is very important in magnetism because he discovered, even though accidentally, right? But he discovered the relationship between electricity and magnetism, right? So we're going to talk about that a little bit later on, but the idea here is that he was doing an experiment in his office or in his classroom maybe, and he had a magnet. sorry, he had a compass on his desk. I remember one of the things we have here at this time, which is around 1819, they were well aware of what the compass is, what it does, that it does, it detects the Earth's magnetic field, and it aligns itself with Earth's magnetic field. And if there are no other magnets around the compass, it only detects Earth's magnetic field and points in that specific direction. So let's say if you're a high school teacher, and he was a high school teacher, doing an experiment, and you have a compass, you should exactly know where north is, let's say, and where the compass should be pointing. So one thing he did, he was doing an experiment where he had a, let's say, circuit with wires connected to some kind of, basically he had a battery, right? He had some kind of load, and wires connected to that load, and there was the electric switch. So he was demonstrating how you can have a current in a circuit. So one thing he discovered here is this. So as soon as he closed the switch and there was a current running through the wires, he noticed that his compass started fluctuating. That means there's compass detects new magnetic source, but he looked around and there was no magnetic source on the table. So he was surprised. He opened the switch to see what's going on. As soon as he opened the switch, he noticed that compass went back to pointing north. He closed the switch again, which means that current started running in the circuit. Compass again started fluctuating and pointing in some random direction, which is one of the things we'll see, is that magnetic field is a vector. So when there are more than two magnetic sources, well, the compass points in the direction of the net magnetic force or net magnetic field. So that's why one of the things we have here is he discovered that if you have a wire and there's a current running through the wire, it acts like a magnetic source. All right. So electric current in a wire detected a nearby compass needle, or deflected nearby compass needle. It can only do that if it, generating magnetic field. So that's why he discovered that electric current, which is, you can think like electricity, generating magnetic effect. All right. So which is a very important, because it's a relationship between electricity and magnetism. Up to this point, they had no idea they're related in any way. You can see, right, we're talking about 1819. So we had really good understanding of electricity at this point, and relatively good understanding of magnetism, but we consider them to be separate branches of physics. And here we discovered that, wow, they're actually related. We can relate electricity or generate magnetism using electricity. So those are one of the important discoveries, right? Like you can think of associated with Ørsted, even though it's a important discovery, it was by accident, and probably some of the very important let's say discoveries were done by accident. Well, in any case, so it was an important discovery, and then it opened new branch of kind of like, let's say, field where instead of electricity or magnetism, we call it electromagnetism, where a lot of them scientists, mathematicians started working on putting them together, finding the unified theory, or finding how those relationships work. And we have André-Marie Ampère, which you can see Ampere, which is the unit for current, amps, right? Comes from after him. So he deduced quantitative laws of magnetic forces between current carrying conductors. So this is also very important. That means one of the things he discovered is that, so let's say if you have a current and the wire with the current running to that wire, one of the important things he discovered is that the magnetic field generated by this wire, assuming it's a straight wire, right? Magnetic field generated by this wire actually goes around this wire. So it's kind of like, it's a curling magnetic field. So something like that, right? So where there's a specific direction depending on which direction is the current. So that means if you have a wire, the magnetic field, or think of like magnetic field lines, right, go around the wire in a circular path like that. All right. So that's why it's a curling sort of effect, where let's say if you have an electric charge, electric field is like sort of like a straight line like this, right? But magnetic field kind of goes around. It's in a circle like that. So that's one of the things he discovered, and he found a equation to describe that. Also, he discovered that since this is a source, magnetic source, and let's say it generates magnetic field everywhere in the surrounding area. If you bring another wire with the current, well, they exert force on one another. Just like when you have two sources, right? Two electric sources, they also exert force on one another. So, and he was able to deduce the equation that allows you to find the forces between two sources like that. All right, so anyways, we will come back to this. We will come back to his discoveries, look at some of his equations. So, but anyway, so you can see, right, suggests that electric current loops of molecular size are responsible for all magnetic phenomena. This is a little bit more advanced, right? That means, inside the wire, inside the current, right, there are, the magnetic phenomena is because of the, electricity. All right, so some of the later discoveries were done going back, in opposite direction. So basically, okay, so electricity generates magnetic field. Well, can then the magnetic, object, generate electricity? So those were the, discoveries done by Michael Faraday and Joseph Henry. So they, again, did more experiments on, looking into the relationship between electricity and magnetism, but they were looking in another direction. Would magnetic field generate electricity? And obviously, since we're talking about them, they were successful, and they were very successful, because we're going to talk about Michael Faraday, especially in chapter 23, and some of his discoveries we're still using, and we'll talk about that. But he was able to show that you can generate electricity with magnetism, and that means if you have magnetic fields, right? That means magnetic sources, you can generate electricity. Okay, so but there are some very important things that we have to discuss, let's say, in terms of this. Again, we will come back to that idea in chapter 23. All right, so at the end, we have James Clerk Maxwell. So you can think of like, he was similar to Isaac Newton, who took everything that was before him, like let's say Galileo's work, Kepler's work, and things like that, and unified them into this laws of motion. So we started as 3 laws of motion, Newton's laws of motion, right? But remember, some of these laws not necessarily was his. Some of them was by Kepler, some of them was Galileo and others, right? But he unified them. He put it in much more mathematical format and things like that. Same thing we have for Maxwell. He took all those discoveries, all those concepts, let's say, we're going to cover most of those things here. So, and he put them in 4 equations called Maxwell's equations, all right? And all those equations basically represent everything, or everything like electricity, magnetism combined, like electromagnetic phenomena. So, and we're going to be looking at some of them in this class. We actually do look at, even though they are more a very calculus or vector calculus heavy, but this is a calculus based class, and we will be at least briefly looking at some of them. All right, so one of the things I kept talking about here, magnetic field, right? But let's look at in terms of how do we generate that magnetic field. Remember, so there are electric fields generated by an electric source. Now there is a magnetic field generated by a magnetic source. And there are a lot of similarities. That means, in terms of when you look at electric sources, or they generate electric field, and magnetic sources generate magnetic field, there are a lot of similarities, but there are a lot of also differences. So we're kind of going to talk about that, and kind of talk about, like, let's say, what is a magnetic field, how to generate magnetic field, and then similarities between electric and magnetic fields. All right, so you can see, right? So for example, in order to generate a magnetic field, you need a magnetic source. So one source of magnetic fields is the bar magnet or permanent magnet. That means this is the same magnet that, let's say, you use on your refrigerator. Those are called, permanent or bar magnets. And they always have, north and south poles. And, remember, there's no such thing as magnetic monopoles. So that means every magnet, right, eventually has those, 2 poles. And one thing we have here is the magnetic field always kind of, you can think of like, let's say, going from north to south. Okay, it's always going from north to south if you're talking about like outside of the magnet. So one of the things we can see here in this picture, right, is that the magnetic field starts from north, or at least in the picture shows that there's those green lines, right, from north, and let's say this one here, right, it's from north, goes all the way to south, and you can see the direction. And it's very easy to detect the direction of a magnetic field compared to electric field, because all you need is a compass, and you can just put the compass there and easily figure out the direction of the magnetic field. Because compass needle, right, always points. See, let's say if this is a compass and it's showing in that direction, that means at that point, magnetic field pointing in that direction. Remember, those lines are not magnetic fields. Those are magnetic field lines, which is a little bit simplified picture of those, just like we had electric field line. But one of the things we can do here is if there's a electric field line, we can find the, magnetic field line, or even electric field line, right? You can always find the electric field or magnetic field from the field lines picture by looking at the tangent to the field line to be the electric field or magnetic field. So in this case, you can see, right? So let's say this is the line, and then tangent to that, at that position, right? There's a magnetic field right there. Here's a tangent to that, tangent to this, right? Tangent to that, here's tangent to that. Those are the magnetic fields at that position. So it's right here, this one right here, this one right here. But you can see, right, overall, you can be able to see that it more or less is pointing like that. So this one more or less going in this direction. And that's why we do, let's say here's the magnetic field lines, which is kind of like average path of those fields. All right, so, and you can see that all this, all this area, all this space then will be magnetic fields, generated by that source. And obviously, one of the things we're going to see is further you go from the source, weaker it is. Just like, if you have a charge, right? Let's say here's a positive, here's a negative. See, electric field goes from here to there, like from here to there, right? Remember, kind of like we always talked about that. So that's the direction, right, of the electric field, which is goes from positive to negative. So you can see, right, more or less very similar, picture that we get. So this is, magnetic dipole, this is electric dipole. So this is positive Q, and this is some negative Q, and you have that picture over there. But one of the things we have here is, also in terms of similarities, is that both of them are vectors. So both of them have to treat it in terms of its magnitude and direction. So that's why, let's say, when I'm talking about field, right, I have to talk about, like, let's say, here's that field in terms of magnitude direction, right? So if I have something right there, that's going to be maybe tangent to that, but a little bit weaker because it's further from the source. So the direction of the magnetic field vector at any location is the direction in which the north pole of a compass needle points at that location. So that's why for us, finding the electric field in this, in this picture over here was a little bit difficult. So we had to use that potential difference and things like, remember, we used that equipotential lines to get this picture, okay? But magnetic fields are much easier because we have that tool, right? So let's say, the compass, and we can always use the compass to figure out in which direction the magnetic field is pointing, or magnetic field lines are going to, okay? So you can see, right, magnetic field lines can be used to show how the field lines as traced out by a compass would look, okay? So that's kind of like, one very similar, in terms of like electric field and magnetic field. Another very, interesting thing that you can do to figure out the directions, which, I usually, when it's a face-to-face class, I do this in class because it's a relatively straightforward. So you take iron filings and, you take a bar magnet, put the iron filings, and you can see exactly, this picture over here. So you can see kind of like, I can get rid of mine. So you can see this picture over here. You can see, right, bar magnet, and how the magnetic field lines look like. Now, if you look over here, it's the same thing, right? So this is north, this is south. So magnetic fields go like this, right? So you can see the direction, right? So let's say they line up with respect to those, field lines. You can see, right? They line up with those field lines. You don't necessarily see the direction, but, you can use a compass again to find that. And then this is, north and south, because the, magnetic field goes from north and south like this, right? Always pointing in that particular direction. So, so let's say like this, like that. So, and of course, it goes into its own, south, but, let's say there's you can see the entire region is filled with the magnetic field lines or magnetic field. So that's why all those iron filings line up perfectly, right? With respect to those. And this is, north-north, so you know how to kind of repelling, like charges, okay? So magnetic field at some point in space can be defined in terms of magnetic force. Okay. So we find, obviously, there is a magnetic field, there is a magnetic force, just like if there is an electric field, there is electric force. Okay. And what we can do here, we find the following result, which are similar to electric forces for a force exerted on a moving charged particle. Okay. Remember there, we talked about in terms of if there's a source charge, let's say some Q, remember that generates electric field that is, moving away from that source charge, right? So, and the entire region then is filled with electric field generated by this charge. Yeah, further you go, weaker it is, but still the entire region technically is filled with those electric field lines. Now, if I bring a test charge, if I bring some kind of test charge, then if I put that test charge with some distance r from that, source charge, right? Remember, there's electric force, right? There's electric force acting on it. And we talked about that, right? So then this electric force, basically, if I know that electric field over there, then I can find the electric force by taking the charge and multiplying by the electric field. So this was the, relatively simple equation, right? That we can use to find the electric force. If there's an electric field and there's a test charge, with some finite distance from the source charge, then there's a force acting on it. It's going to be either pushed or pulled. That means it's in the direction of the electric field or in the opposite direction of electric field, because electric fields are radial, right? That depending on charge source configuration. So if your test charge same as source charge, force is in the same direction of electric field and being, let's say, pushed like that, right? So this will be then electric force, in the same direction as electric field, so being pushed by the source charge. All right, so then in terms of the magnetic forces, okay, there's a little bit of differences there, okay? So we're gonna first talk about, let's say, similarities, and then we're gonna talk about differences. So you can see, right? So similarity is that if there is a magnetic force, if there's a magnetic field, there's a possibility of magnetic force. Just like if there's an electric, field, there could be an electric force. So now, one of the things we have here is this. For the magnetic force, well, it has to be a charged particle, okay? And it has to be charged particle, just like the electric force. It's only acting on charged particle. Remember, if there's an electric field, you bring a neutral object, so then depending how far away it is, right? If it can polarize it or something like that, it can, let's say, eventually, right? Remember, I can show you that kind of can do that, but mostly it requires the effect that we can actually calculate. We need a charged particle. All right, so then the charged particle, if you remember, you can see this equation that I gave you. You can see, right? Electric force is proportional to the charge, test charge, right? So bigger the test charge, bigger the force, right? So remember, if I have an electric field of 10 Newton per Coulomb, then you can see, right, the force equals 10 Newton per Coulomb, which is the same for that position, right? P times the test charge. Well, if you have a 10 nanocoulomb test charge, then it's 10 nanocoulomb times 10. 100 nanocoulomb test charge, it's 100 times 10. So that means it increases or directly related to the charge. Bigger charge, bigger force. That's what we have. That means similar way, right? Magnetic force is proportional to the test charge. Okay, so magnetic force is proportional to the charge Q of the particle. Bigger the charge, bigger the effect, this magnetic force effect. Also, one of the things we have is that magnetic force on a negative charge is directed opposite to the force on a positive charge, moving in the same direction. Well, that's also important to understand. Well, this was also true for the electric forces, right? So remember, if this is a positive charge, so remember, if there's an electric field like this, so the positive charge, again, this is positive, has a force in that direction, but for the same electric field, you put a negative charge, the force is in the opposite direction. Because remember, positive and negative charges are being pulled or pushed, right? So that means, the force is in the opposite direction. Same thing for the magnetic force. So let's say, for example, if this is a positive test charge, one very important thing, I'm kind of jumping ahead, but one very important thing about magnetic force is that it requires particle to move. So that's why before, when we were covering electrostatic, we could completely ignore magnetic phenomenon, because stationary particle doesn't feel any type of magnetic phenomena, magnetic force. But let's say, for example, if there's a particle moving with some velocity, if it's positive charge, let's say, and this is a force acting on it, and if this is the same particle moving with this velocity, nothing changes. Let's say there's a magnetic field, same direction, there's a velocity in that direction. If this is a negative test charge, then force will be in the opposite direction. Okay, so that's kind of like the force is different direction depending if it's positive or negative charge. Also, the magnetic force is proportional to the magnitude of the magnetic field. Well, that's also similar to the electric force, right? See, electric force proportional to the charge, but electric force also proportional to the electric field, right? So that's why F equals Q times E is proportional to, directly proportional to charge and electric field. Well, same way, magnetic force is directly proportional to B, which is the magnetic field. Okay, so capital B is for the magnetic field. That means they are proportional to one another directly. Bigger the field, bigger the force. Bigger the charge, bigger the force, right? Kind of similar to that. All right, so the differences here also, now, let's say several differences. Main difference here is that particle is let's say your positive, let's say positive source charge that has a electric field, right? Or some sort of like electric field in this region. And here's what we have. So let's say to feel electric force, all I have to do is bring some kind of test charge and place it there. I can just drop it there, or I can just put it there and let go. That means regardless if that particle is at rest or if it's moving to the left, right, up, down, at rest to start with, there's going to be electric force right away on that particle. That electric force, because this is positive, right, will be repulsive and will be in the direction of electric field. So regardless of what the state of motion of that test charge, there's electric force on it. But it's really different if you have, let's say here's a magnetic field from some kind of source, right? So I place a test charge with no velocity, right? So I put it there and let go. That guy can just sit there forever. There's absolutely no force acting on it. So it's not moving. If it's not moving, there will never be a magnetic force. So that's why the magnetic force is proportional to the speed v of the particle, okay? That means F of B, which is magnetic force, proportional to the velocity or the speed. Speed is 0, force is 0. No matter if it's charged, no matter if there's a magnetic field there, if it's not moving, there is no force. So once, let's say it starts moving, let's say it's a moving charge, you still have to actually have certain conditions satisfied. So for example, if I push this particle, okay, like let's say move. So I push it in this direction. So that means the velocity is no longer 0. So now it's moving in some direction. Well, according to this, there has to be a magnetic force, but this is only one of the conditions. Remember, so you have this condition 1, here's condition 2 that we talked about before, right? And then here's condition 3, which means magnetic force depends on the speed. Magnetic force depends on the charge. Magnetic force depends on the presence of the magnetic field, or directly proportional to the magnetic field. But there's also another thing, which is the fourth condition. And that comes from the fact that, magnetic force is quite different from electric force in terms of its, direction at least. So think like this. If I have the magnetic field, the way I have the direction, right? Let's say to the right, and I push the charge, so now it's also moving to the right. And if I try to see if there is any effect from that field on that particle, I'm going to see that there's absolutely no effect. It's going to continue moving like this without being deflected. Remember, one of the things force can do, it can slow you down, it can change your direction and things like that. And electric force, so let's say here's electric force, right? Electric force can do two things. It can change speed, it can change direction. Kind of like running our room. So change speed and change direction. Okay. Now, one of the things we're going to see here is if the particle is moving in the direction of the field, you still have no force. Okay. Because one of the things that we have here is the magnetic field proportional to then the direction of the particle motion, right? The velocity direction relative to the magnetic field. That means there's this, sine of theta, you can think of like that, right? And one of the things we have here is then this theta is the angle between magnetic field and then the velocity. And the requirement here is that theta cannot be 0 or theta cannot be 180 degrees. That means if the particle moving in the direction of the magnetic field, or if the particle moving in the opposite direction, that means the angle between them is 0 and 180, you get no force. Okay, you get no force. That means what you have here is, in order for you to have some kind of magnetic force, the particle has to be moving such that there's some kind of non-zero or non-180 degree theta between them. So, and that means that you can say, right, so that means the magnitude of the force depends on the direction of the particle's motion, right, the velocity direction relative to magnetic force, a magnetic field. Magnetic field and velocity cannot be parallel or anti-parallel, okay? They can be perpendicular, that can be at any angle, but 0. So those are the two angles where the magnetic force is 0, okay? And one important thing also we have about magnetic force is that magnetic force is always perpendicular to the plane formed by the velocity and magnetic field. So for example, let's say here's a plane where I have a particle. So what I have here is I have a particle moving like this with this velocity. This is basically on the plane. But what I also have here is then, I have then, let's say, the magnetic field in the plane like that, right? So let's say there's a magnetic field like this in this direction. This is the direction of magnetic field. Both of them on the plane, okay? So here's a velocity, and then here's a magnetic field. Then magnetic force has to be perpendicular to both velocity and magnetic field. And since magnetic field and velocity are perpendicular on that plane, that means force has to be outside of this plane. That means force either going to be out of the plane, pointing out of the plane like this, or upward, right, or downward. But it cannot be on the same plane. So that's why it's perpendicular to the plane that is, where you have your velocity and magnetic field. Okay, so again, here's a little bit better picture than what I have. So think like this. So let's say there's a magnetic field in that direction, right? Those greens are magnetic fields. Let's say that region is filled with magnetic field, and you have a positive particle moving in that direction. Okay, red is the direction of the velocity. So you can see, right, you have a velocity, non-zero, check. You have a magnetic field, non-zero, check. You have a charge particle, so check. Now also you have a theta that's, neither 0 or, 180. So basically theta that is not equals to greater than 0, but less than 180. Anything works as long as it's not 0 and non-180. So if those conditions satisfied, there is then magnetic force. And then magnetic force, you can see that has to be perpendicular to velocity and perpendicular to magnetic field. That means it cannot be on the same plane as those two. So it's, let's say, out of the plane, okay? So those are the things, that's why it's a whole lot more complicated. So electric force is so simple. So here's electric force equals Q times electric field, that's it. All you need is charge and electric field, okay? And it's regardless, if it's a moving charge, if it's a, let's say, stationary charge, that's it. That's the magnitude. And, for the electric force, right? So you can say F equals Q times E, that's the magnitude. If you kind of do it like that, right? And then direction is always, remember, if Q is positive, F and E have the same direction. If Q is negative, F and E have opposite direction. It means force is pointing in the opposite direction of electric field. So now you can see how simple this was. Magnetic field is more complicated. That means it needs a moving charge. there's a magnetic field has to be there. There has to be, charged particle, and the particle has to move moving such that it's not parallel to the velocity. And the magnetic force has to be then always perpendicular to the plane of that. So that's kind of what we have. So you can say, right, the magnetic force is distinctive because it depends on the velocity of the particle. Its direction is perpendicular to the velocity of the particle, and because its direction is perpendicular to both velocity and the field. Okay, that means it's always going to be in a, kind of like perpendicular to both and out of the page or into the page. Okay, so that's always going to be the case. All right, so then here I give you the equation. So kind of like, let me kind of summarize it. So you can do like f of b is, remember, it's proportional to q. I put q naught because it's test charge. It's proportional to velocity, proportional to magnetic field, right? So velocity, or the, q, charge, speed, magnetic field strength, and sine of theta, or angle is between velocity and magnetic field. Okay, so this is the equation for the magnitude. So this is magnitude. Okay, which is QVB sine theta. And hopefully you remember we have seen, something like that in previous chapters. Mainly, like, let's say a format where you have two vectors, where technical velocity is a vector and magnetic field is a vector, and it's a product of two vectors. Q is a scalar, but it's a product of two vectors, V and B. And the resultant is product of two vectors times sine of angle between them. All right. So this is nothing but a cross product or a vector product. So it's Q times V cross B. So that's why we're going to see in the next slide, the cross product. And we had something like that, right? So the torque was technically a cross product. So remember, it was R cross F, right? So it was a cross product. So that's why we could write this as RF sine of theta. Okay. So same thing, right? So magnitude of first vector, magnitude of second vector, and the sine of angle between them. Same thing. Here, just Q again is a scalar, right? But it's Q times V cross B, where V cross B is magnitude of the first vector times magnitude of the second vector times sine of angle between them. All right. Anyway, so this is more vector format equation, right? But that means you can always do this. You can just use this equation to calculate the magnitude first, which is QVB sine of theta. Okay. And then find the direction, which we can do mathematically, find the direction. Also, we can do using what we call the right-hand rule, okay? All right, so the units of magnetic force is newtons. Obviously, it's a force. But units of magnetic field, which we haven't talked about that, right, is Tesla, after, Elon Musk company Tesla. Well, not quite, right? So it's not after the company Tesla, but it's after Nikola Tesla. So who was quite late, right, to this, discoveries of magnetic and electric phenomena, but he did so many discoveries, so much contribution that magnetic field units actually is after him. And I mean, imagine how important his contributions are, that, the previous unit for the magnetic field, which was in, we still use it in CGS units, right, was Gauss. And Gauss was a giant in mathematics and physics, but Tesla basically replaced the units for magnetic field, right? So we call that, basically we use Tesla. You can see, right, 1 Tesla equals 1 newtons times seconds per coulomb times meters. And that's basically, you take that equation rearranged, and this is what you will get. All right, so here's kind of how you do the the right-hand rule to find the direction of the force. So you can see, right, there are 2 right-hand rules to determine the magnetic force. And I usually use this one here. You can see in this diagram. So you first, let's say you have your fingers, let's say in the direction of the velocity. Okay. So your fingers point in the direction of the velocity. And then what you have here is that the palm then faces the field. So velocity, then palm faces the field. And then what you do here is you're going to need to be able to curl your fingers from the direction of the velocity to the direction of the magnetic field. So that's why it's a curling, kind of motion. So as you curl, from velocity to magnetic field, your thumb then will point in the direction of the magnetic force, right? So curl your finger in the direction of the field, thumb point in the direction of the cross product, which is the magnetic force in this case, all right? So generally this right hand works for the positive test charge. So if your test charge is positive, your right hand gives you the direction of the velocity, you curl in the direction of magnetic fields, force is direction, of your thumb. And that means any positive charge is gonna have a force in the direction of your thumb. One thing you can do here is that you can do the same thing, same right hand rule. The only thing, if you know that your test charge was negative, then, use the right hand rule. You just take the direction of the force opposite of the direction of your thumb, okay? That means, for example, here, if this is a positive test charge, the force on it is gonna be up, okay? The same direction as your thumb. If this was a negative source charge moving in that direction, right? And there's a magnetic field in that direction, then magnetic force will be down. So it's gonna be pushed down for that because of that magnetic field. All right, so again, this is the magnitude of that, force, Q in absolute value, to make sure that magnitude is always positive, right? QVB sine of theta, okay? Again, theta is the angle between the velocity and the field. And then the force is 0 when the velocity and the field are parallel or anti-parallel. Assuming that it's moving, assuming there is charge, assuming there is magnetic field, you still have to move such that you are not parallel to the magnetic field or in opposite direction of the magnetic field, right? Only then there is a force, which is again then perpendicular to the magnetic field and velocity vectors. So that's why, a little more, extra things to kind of keep track of. And obviously one of the things you have is that there's a maximum amount of force acting on the particle if it's moving perpendicular to the field. So let's say if this is the field, let's say magnetic field, and let's say here's a positive charge moving, with this velocity perpendicular to the magnetic field, the force acting on it then will be, maximum compared to, let's say, if it was moving in this direction. So I'm gonna give you 1 second to, few seconds to figure out the direction of the force. So let's say using the right hand rule, try to come up with the direction of the force acting on this particle, okay? That means take your fingers in the direction of the velocity, then curl your fingers in the direction of the magnetic field, and then see where your thumb is pointing, okay? So do that. All right, so hopefully you got into the page as your direction of the force. All right, if not, go back and watch it again in terms of how I, able to find the direction. So your fingers in the direction of magnetic, the fingers in the direction of the velocity, your palm is pointing in the direction of the magnetic field, right? Facing magnetic field, but then you're gonna need to be able to curl in the direction of the field so that your thumb then is into the board or into the page. All right, so again, so here are some important differences between electric and magnetic forces on charged particle. Electric force vector is along the direction of the electric field, whereas the magnetic force vector is perpendicular to the magnetic field, right? So that's very, important, difference. The electric force acts on a charged particle regardless of whether the charged particle is moving, whereas magnetic force acts on a charged particle only when the particle is moving and doesn't have a 0 theta or 180-degree theta, okay? The electric force does work in displacing a charged particles, whereas magnetic force associated with a steady magnetic field does not work when a particle is displaced. Now, I'm sure you were able to follow the first condition and second condition, but not sure if you can, visually understand what this one does. If you did, perfect. If not, what do we mean by, it's not able to do work? Well, remember one thing about work. See, work, when you do work, right, you change the kinetic energy of the object. That means there is a final and initial kinetic energies that are not the same. Well, remember, if the final kinetic energy is not the same as initial kinetic energy, what it means that you're doing work and your work goes into changing the speed of the object, right? If the kinetic energy is increasing or decreasing because the speed is changing. Well, we talked about, right, that electric force can do work. And, because there's a potential energy, right, associated with that. And it can go and change the kinetic energy of the object as well. Electric force can make you speed up and slow down, can change your direction, any of those things. But what does it mean when you say that work done by, let's say, magnetic force is zero? It doesn't do work. Well, if the work done is zero, means delta K is zero, which means that K final is same as K initial, which means V final is same as V initial. And that's very important. That means whenever there is a magnetic force acting on the particle, I mean, there's a magnetic force acting in the, affecting, it doesn't change the speed. What? So what does then do when there's a force acting on it? Well, remember, the force will always change your velocity, but your velocity can be changed by changing magnitude, which is the speed, or changing direction. Electric force can do both. Magnetic force can only do one of those things. And clearly here we talked about that it cannot change your speed, because when magnetic force doing work, that means it's, acting on the particle, well, particle doesn't, speed up or slow down. But particle will change direction because of the magnetic force. And that's some of the things we're going to be seeing in a little bit. All right, so since we are going into more or less three-dimensional systems here, because it's X, Y, and also Z, right, out of the page or into the page, a lot of times we might have magnetic field to be into the page or out of the page. And a lot of times that's a little bit easier even for us to kind of consider. So here are two ways I can represent magnetic field to be into the board and out of the board. And what we have here is, think of like this. Magnetic field is a vector. So think of like you looking at the vector, represented by an arrow. And when the magnetic field is coming out of the page, you're looking at the tip of the arrow. And then here you have that, right? So think of like those dots, right, are the tip of the arrows coming out of the page. So that means that's why you have magnetic field out of the page, and those dots represents the tip of the arrow where the magnetic field coming out of the page. That means all that region is filled with uniform magnetic field coming out of the page. Same way I might have the magnetic field into the page. Well, still it's a vector, it's represented with an arrow, and then I'm looking at the back of the arrow, right, when I'm looking magnetic field into the page. And that does, this X signs are actually not X, but back of the arrow, sort of like, let's say. And that just represents magnetic field going into the page. So be in always going to represent, magnetic field into the page, okay? So because one of the things I can do here is, let's say now I have a magnetic field, let's say case one, right? Magnetic field out of the page. And let's say here I have a particle moving with some velocity V, okay? Then because the magnetic field is pointing in a Z direction, velocity is pointing in an X direction, then more or less, remember, magnetic force has to be perpendicular to velocity and magnetic field. So it has only one axis to be on, right? So because velocity is horizontal, B is on a Z axis, that means force has to be in a vertical axis. And using the right-hand rule, right, you can see that if you have the velocity to the right, your fingers pointing in a direction of velocity, your palm facing the direction of magnetic field, and you curl in the direction of magnetic field, you will see that force here is acting down. So force here, pointing in a direction, negative Y. And that's going to make the particle deflect toward that, okay? And the same way, right, if I have a particle here moving with some velocity V, same thing, right-hand rule, fingers in the direction of the velocity, you curl into the page, right? Because that's what the magnetic field is. Force then will be in this direction. Sorry, this is magnetic force. And that magnetic force is going to deflect it like that, okay? That means magnetic force, you can see, right, perpendicular to both velocity and, magnetic field. So that's why it's always easier if the magnetic field is actually out of the page or into the page, because then the force will be on the XY plane. All right, so a couple of rules on cross product or vector product. So remember, these are notations, just A and B and C are some, dummy variables, right? Those are vectors. So when you do A cross B, that means you have two vectors. Here's vector A and here's vector B. And the best way to do here is connect them at their tails, connect them at their tails, and then theta, see, they represent angle between those two, right? So angle represents, theta is angle between those two. And to find the direction of the, resultant, right, the cross product, you use the right-hand rule. See your fingers in the direction of A. So if you do your fingers in the direction of A, and then you curl them in the direction of B, you get that. Your thumb is pointing up. And this is A cross B, because you start with A, your fingers in the direction of A, then you curl in the direction of the B. So remember we talked about dot product as well, which was A dot B, all right? So this was a scalar quantity, it didn't have a direction. So all we had to do is just calculate the magnitude. But one other important property for the dot product was that B dot A is exactly the same as A dot B. Well, that doesn't work for the cross product, because if you start with magnetic field, sorry, this B is not magnetic field, it's just basically some dummy variable. So if you start with B, your fingers in the direction of B, and you curl in the direction of A, so try to do that. So your fingers in the direction of B, then you curl in the direction of A, you can see your thumb is actually pointing down. That means if you do B cross A, you're gonna get same magnitude C, but in the opposite direction. So that's why what we have here is A cross B equals negative B cross A. Okay, so they are opposite. The resultant end up being in opposite direction. Okay, so that's, you can say, right, not commutative. That means A cross B is not equals to B cross A, but negative of B cross A. Okay, and also one of the things we have here is if A is parallel to B, then A cross B is 0. Remember, because one thing we have here is this, right? A cross B has a different notation where if you know the magnitude of A and you know the magnitude of B, then you can multiply magnitudes times sine of theta between them. Well, if theta is 0, sine of 0 gives you 0. If theta is 180, sine of 180 gives you 0. That's why cross product between any two parallel vectors always going to be 0. But cross product between two perpendicular vectors give you the maximum, let's say the magnitude, right? That's why if A is perpendicular to B, then A cross B becomes just AB, because, perpendicular means theta is 90, sine of 90 is 1. All right, so here a couple of other, let's say algebra rules. You can look at them. We don't necessarily work with them so much. Maybe in a higher level we work with them, but in this class not necessarily. So you can kind of look at them, but they're not really used in this class. Okay, but what we use a lot are those unit vectors. Okay, and one of the things we talked about before, if you remember, I hat was equals to 1, because when you have a unit vector, remember, here's I hat, here's another I hat, so you have two I hats, right? And remember, if you do I hat, that meant you are doing dot product. Remember, dot product was this: magnitude of the first one, which is 1, times magnitude of the second one, which is also 1, times cosine of angle between them. And two I hats are parallel, so cosine of 0 degree. So I hat was equals to 1. Okay, so this was the dot product, but we're not using that. So we're doing I hat cross I hat. And the equation for I hat cross I hat is this. Well, magnitude of 1 times magnitude of the second one, which is also 1, then times sine of the angle between them. But two I hat vectors are parallel, which means there's 0 degree between them, right? Well, you get 0. Same way if you're doing J hat cross J hat, well, J hat cross J hat, magnitude of 1 times magnitude of 1 times sine of 0 degrees, you get 0. So you can say, right, I hat cross I hat equals J hat cross J hat equals K hat cross K hat, you get 0 for that particular reason, because, well, cross product of any parallel vectors are 0. And then you have this. So you have I hat cross J hat. Okay, they are perpendicular. So when you're doing this, you are perpendicular. But remember, when you do I hat cross J hat, the resultant has to be perpendicular to either one of them. And the only thing that's perpendicular to I hat and J hat is K hat, which you can kind of see it yourself, right? So think like this. If you have I hat, and then you can have J hat. So use the right hand rule. Take your fingers, point in the direction of the I hat. And so that your palm is facing J hat. And then you curl your fingers in the direction of J hat. And you will see your thumb is pointing in the direction of the K hat. So that's why if you do J hat cross I hat, which is your fingers in the J hat, cross I hat, well, it's now going to be then negative K hat, right? So play with that, then you can be able to, understand all of those things. But you can see, right, I hat dash J hat has to be K hat. J hat cross K hat, well, it has to be the vector. There is neither, J or K, it has to be perpendicular to them, and that's I hat. Okay, so that's why, in terms of if you have I hat, J hat, the result is K hat. But you have to be careful. Are you going from I hat to J hat, or are you going from J hat to I hat? So you can get, like, let's say, opposite direction. All right. So in any case, so work with those. Play with your right hand. Right. Try to understand how the unit vectors are related, because mathematically we can a lot of times just find the direction of the force if you're using that vector version of the equation directly. Okay. So here's an example. So it says two vectors lying in the xy plane are given by the equation a equals 2I hat plus 3j hat, and b negative I hat plus 2j hat. Find a cross b and verify that a cross b equals negative b cross a. That means we're going to do calculation to basically verify this particular value for the magnitude direction for the a cross b, calculate the magnitude and direction of b cross a, and see that there are basically reciprocals. Okay, so here's how we would approach that. So there are several ways you can do that. So you have a 2I hat plus 3j hat. See, remember, if you have the magnitude of a and magnitude of b, and angle between them, you can just put ab sine theta, the easiest one. So technically you can do that, right? Because you have the components of a, components of b. You can find a, you can find b magnitudes, you can find direction of a relative to positive x, direction of b relative to positive x, find their relative, let's say the angle between them, then use simple equation ab sine theta. All right. So, but whenever you given components, sometimes you just maybe like easier just to go through that, the equation itself. So here I have a cross b. Okay, a is 2I hat plus 3j hat, and cross negative I hat plus 2j hat. Okay, so what we get here is this. So I'm just basically distribute this, right? So 2I hat cross negative I hat, right? Then plus. Then 2I hat, oops, sorry, 2I hat cross 2j hat. Okay. Then plus 3I hat cross negative I hat. Then plus 3j hat cross 2j hat. Okay, so I'm going to continue here. So then what I end up here, for example, this one becomes negative 2I hat cross negative I hat. Like that. All right. Then plus. So now this one, so 2 times 2, so I get 4. Then I hat cross j hat. Then this one, I have 3 times negative 1, so it becomes negative 3. Then I had I hat cross negative I hat. All right. Then plus, then this is the last one. Then I have 2 times 2, 3 times 2, that's 6. Then I have j hat cross j hat. Okay. Now, if you remember, those two are, I hats. So those two I hats go to 0. Those two are two j hats. So if you do the cross product, that also goes to 0. Okay. This one's I hat j hat survives. Sorry, here I made a mistake. So this is j hat cross negative I hat. Oh, I actually even take out the I, so j hat cross I hat. All right, sorry about that. So so if basically those two survive, right? So then what I get here is this. Then 4 times, well, I hat cross j hat. So let's look at this. So I hat cross j hat. So if you look at the previous slide, right? So this is I hat, your fingers in the direction of I hat, cross j hat. Well, that's k hat. Okay. Then plus -3. And then this cross product of j hat cross a hat is actually the negative k hat. Okay. Which then gives you 4k hat. This negative cancels that negative, plus another 3k hat. So you get 7k hat. All right. So you get 7k hat. And that's basically the answer for this cross product. So whatever, let's say this cross is the C, right? So the C is the product, right? Has magnitude of 7 pointing in a positive Z direction. Okay. All right, so let's do this then. Let's do then the other one, right? B cross A. So if I do B cross A, I want to see how they're related to A cross B. All right, so if I do B cross A, so then what I get here is 2I hat plus 3J hat, then cross, then, sorry, negative I hat plus 2J hat, cross 2I hat plus 3J hat. Okay. So then what I get here is -2 I hat cross I hat. If I do, the first one, and then plus -3 I hat cross j hat, then plus, then I get 4 j hat cross I hat, then plus 6 j hat cross j hat. All right. So then from here, one thing you can see is that this goes to 0, I hat cross I hat. This goes to 0, j hat cross j hat. So I have 2 surviving terms. Okay. So those 2 surviving terms give me this. So this is -3. I hat cross j hat gives me k hat. Then plus 4, and then j hat cross I hat gives me -k hat. And summing them, I get -7k hat. You can see, right? I get exactly the same magnitude, but in a negative k hat direction compared to the positive k hat direction. Right, so you get the opposite. All right, so here's one more example. We find the magnetic force on a proton moving in the positive x direction at the speed of 0.446 megameter per second in a uniform magnetic field of 1.75 Tesla, which is in a z direction. All right, so this is just to demonstrate how to find that general equation. So you're given that it's a proton. That means you have the charge. Q is equals to just E. You're given velocity, which is 0.446 times 10 to the, this is mega, so 10 to the 6 meter per second. And then given then there's a magnetic field of strength of 1.75 Tesla. Now, it's moving in a positive x direction. So technically then this is I hat. And then magnetic field is in a, z direction. So this is then k hat. All right. So you kind of can, look at it in terms of that. So the magnetic field, velocity, perpendicular to one another, and that's a good enough for us to be able to calculate magnetic force, right? So this is Q times V cross B, which is then 1.6 times 10 to the negative 19 coulomb, then 0.446 times 10 to the 6 meter per second, 1.75 J hat. Okay. All right, so what we get here is we multiply all the numbers together, right? So if we multiply all the numbers together, sorry, this is, again, my bad, this is K hat, right? So we'll get 0.125 times 10 to the negative 12. Remember, this is force, so newtons, okay? So, but then I have the cross product, right? So technically it's, I hat cross K hat, okay? And if you do this, right, I hat cross K hat, you can see that this gives you negative J hat. That means the value here is then, it's negative 0.125, 10 to the negative 12 is pico Newton, right? And the direction is J hat. All right, so that's your, magnitude and direction. All right, so that's how we can just directly basically find that. All right. Here's kind of continuing on that note of the magnetic force, changing only your direction, not speed. So we have kind of seen something like that before. Is, for example, I'm gonna kind of like draw this on the right side picture, but kind of like starting from the beginning. So let's say here's magnetic field. Remember, this is into the board, right? So this is into the board. And let's say here's a particle moving with this velocity. All right. So let's say at that instant we are looking at here's a particle with this velocity and be in magnetic field. Well, remember, if you look at this, right, use the right hand rule, you will see that there's a force in this direction, right? Well, the force you can see, right, it deflects the particle in that direction. That means to the left. So particle gonna be deflected like this. And here, the particle now moving with this velocity. Well, in that case, the magnetic field and velocity together gonna combine, if you do use right hand rule, gonna give you force in that direction. Well, if that's the direction of the force, then it's going to deflect it toward there, right? So it's going to be deflected like this. So then let's say particle now here moving with this velocity. Well, if you do the combination of magnetic field velocity using right-hand rule, you will see there's a force in that direction, which means that it's going to be deflected like this. Again, here's the velocity of the particle, magnetic field into the board. Right-hand rule tells you here's a magnetic force. And we're going to deflect it like this. And what happens here is you might be able to see that what you get here is particle moving around in a circle. And look at the direction of the magnetic force, pointing toward the center. And I'm pretty sure you guys remember, right? If you have a force pointing toward the center, and that force makes the particle go around in a circle, and remember, magnetic force doesn't change your speed. That means particle goes around in a circle at a uniform, constant speed. Hopefully you guys remember the name for this type of force that makes you go around in a circle, maintain your same speed, but change the direction constantly. And let's say going around a circle radius r, and always pointing toward the center. We'll call this a centripetal force. So then centripetal force, right? So the centripetal force always responsible for changing the particles, just the direction. It never changed the speed of the particle or speed of the object, just the direction. So that's why the magnetic force is centripetal force, because it doesn't do any work. And the reason here it doesn't do any work is this. See, for example, remember the equation for the work. It was, if you remember, that was a dot product, right? F dot D, let's say. That means force times displacement. And remember, because this was technically FD cosine theta, requirement was that F and D have to be, such that they're never perpendicular. But for example, here, if I'm talking about just small displacement element, and look at the force, perpendicular. Small displacement element, look at the force, perpendicular. Even here, right, small displacement element, force is perpendicular. Well, that means force and displacement vectors always perpendicular to one another. That's why work done is zero. Work done is zero means you're not speeding up, all right? So magnetic force always points in the direction toward the center and makes the particle go around in a circle like that. Assuming that there, the particle is basically moving such that it's perpendicular to the magnetic field. It's going to be then trapped in that circle, right? Kind of go around like that. Okay. So one thing, hopefully you remember that those centripetal forces, or sometimes we call it radial forces, right? So the equation was mv squared divided by the radius, okay? And the reason, because the centripetal acceleration was defined as v squared over r, and then force is mass times the acceleration, so it becomes mass times speed squared over r. And what we're saying here is this: now magnetic force is a centripetal force, okay? Magnetic force is a centripetal force. That means it equals also to mass of the particle going around in a circle times its speed divided by the speed squared divided by the radius. But we also know this: magnetic force also equals to q v b sine of phi, let's say, or sine of theta. But let's say if they're perpendicular, so technically you can say this: mv squared over r equals qvb, assuming that, let's say, theta here is 90 degrees. Then what we get from here is we get this relationship, right? Then one of the things I can do here, I can cancel this v on both sides. And what I get here is this: mv over r is equals to q times b. And this equation technically can be used to calculate any of those variables, because you have the mass, you have the speed, you have the radius, you have the charge, you have the magnetic field, right? So for example, I can use this equation to solve for the radius of that circular motion, right? So circle of that circle. So which is going to be then m times v divided by q times b. And sometimes, let's say, you can put the absolute value because there's no such thing as negative r, right? So even if it's a, let's say, negative charge, okay? And one of the things you can see, right, that r is here is proportional to the, this quantity, m times v. And if you remember, mv was nothing but the momentum of the particle, right? So in a way, I can write this as p divided by q times b, right? Momentum divided by the charge times magnetic field. All right, so anyway, so this equation, this one over here is very useful because you can relate any of those things, okay? One other thing we can do here is, remember the speed or velocity divided by the, r, right, the radius? Well, that was the angular speed, right? Remember, we had v equals r times omega. Linear speed equals r times angular speed. Well, I can use this, put it in the previous equation, and what I get here is equation for omega, because qb over m, which is even independent of the radius, right? So this is known as angular speed, and this is for the cyclotron frequency. So the cyclotron is a device that we can use, right, for the magnetic phenomena, right, magnetic effects, and this one represents the frequency for that. Well, if you remember, there's also linear frequency, which is then technically omega over 2 pi. You can also relate this equation of that. And where there's a linear frequency, there's always a period, and then there's an equation for that as well. Remember, so period here is then 1 over frequency, right? Or technically, in terms of 2 pi over omega, right? Well, if it's 2 pi over omega, and omega is v over r, then you can also have this equation. Or we can think of, like, remember, if you go around in a circle, right, with speed v and the radius r, then this speed, which is the speed of the particle, right, assuming it's constant, it equals to distance over the time. But if the distance is 1 full cycle, then it's 2 pi times radius, because it's the circumference. And the time it takes for 1 full cycle is the period, 2 pi over t. And then you rearrange that, and then you get basically this equation. And v and omega related, you get that. And since you have the previous equation, right? So if you remember, right, so you have like, let's say this mv over r equals qvb, sorry, qb, right? So mv over r equals qb. If you then replace v with 2 pi r over the period, right? Q pi r over the period, then what you end up with is this. So m 2 pi, because r is going to cancel out, right? Over the period equals qb. And then you can think of like, here's another equation that is independent of the speed, right? Kind of like you substitute for the speed. So mass times 2 pi over the period equals, qb, right? So you can also have this particular equation, right? So anyways, there are several ways you can kind of rearrange this, right? One other thing we can see here is this. So if velocity is perpendicular to magnetic field, then particle is trapped going around in a circle. But what if the particle has, let's say, not only perpendicular, but a little bit of parallel component too? That means instead of, let's say, being trapped going around in a circle like that, then it can kind of go, because there's a little bit of component, right? It's going to go more like a helical path, okay? More of a helical path. So that's why, because there's a component, in a direction such that it's moving along that field line. So it's still trapped, but at least it's not trapped in one space, right? It's kind of moving along the field lines, in the direction of the field lines, if it's positive, or in opposite direction if it's negative. All right, so let's look at then this example here. So you have an electron at point A as a speed of 1.41 times 10 to the 6 meter per second. And what we want to find here is the magnitude and direction of the magnetic field that will cause the electron to follow the semicircular path from A to B, and the time required for the electron to move from A to B. All right. So here's an interesting problem, because this is basically takes into account the fact that particle is in a region where there is a uniform magnetic field, and it's moving with some speed. It's a charged particle, so obviously there's going to be a force. You're not necessarily given the direction of the force, but remember, force is the magnetic force, and you have a path, right, of the trajectory. You're getting the trajectory of this particle. And remember, in which direction magnetic force is pointing? Well, it's always pointing in the direction of the center. That means this is the direction of the force. It means pointing toward the center. That means at that instant, when the particle at point A, there is a force to the right. So then what is the magnitude and direction of the magnetic field that gives you that, let's say, that trajectory? Well, that magnetic field gives you this force, okay? That's why you have that trajectory. And because it's a negative charge, we can use that, let's say, right-hand rule to figure out the direction of that magnetic field, because remember, the right-hand rule will always give you that. But one thing remember here is this. Right-hand rule always gives you what would happen if it was a positive test charge, right? So let's say your fingers in the direction of the field, the fingers in the direction of the velocity. And remember, right-hand rule should give you, let's say, if it was a positive test charge. But this is a negative test charge. So the thumb then should be pointing in the opposite direction of the force that negative charge experiences. That means, for example, if I use my direction of the fingers in the direction of the velocity, my thumb then should be pointing in the direction negative of the force that I drew on the picture. That means, remember, in this example, I'm given velocity and force, and I need to find the field. And the only way I can do that is by understanding that my thumb should be pointing to the left, right? Because, right-hand rule gives you the force direction, which is opposite what would have been in this particular case. So that means my thumb should be pointing to the left, my finger should be pointing up, and when I curl it down, you can see, right, if I curl it in the direction of the magnetic field, it will be curled into the page. That means magnetic field here, everywhere into the page, right? So there's a magnetic field pointing into the page or everywhere in this region. Okay, that's the direction. Next, I need to find the magnitude of that. Well, to find that, Well, I need to understand that what I have here is this. So I'm given the speed. So speed here is equals to 1.41 times 10 to the 6 meter per second. Well, I'm given also the charge because it's an electron. So E minus, we put that for the electron. And I'm given the mass because again, it's an electron, right? So it's 9.11 times 10 to the negative 31 kilograms. Okay. I'm also given diameter of that arc, right, of that semicircular arc, so which is 10 centimeters from A to B diagonal, right? So basically that's the diameter. That means the radius is half of that, or 0.5 meters. That means I'm given plenty of stuff. And I know that centripetal force, magnetic force is a centripetal force, so then I can use that equation, right? I can say it's mv squared over r, but it also equals to qvb. And you can see, right, magnetic field is perpendicular to the velocity, so sine of theta is 1. Again, cancel that. And what I can do from here now is solve for B. So then the B here is equals to M times V over Q times R. Okay. So then B here is equals to, so mass is 9.11 times 10 to the negative 31 kilograms times speed, which is 1.41 times 10 to the 6 meter per second. Then divided by the charge, which is 1.6 times 10 to the negative 19 coulomb. And remember, I'm using absolute value, right? And times then radius, 0.05 meters. All right, so if we do that, we're going to get 1.60 times 10 to the negative 4 Tesla. Right, that's the magnitude. Direction was then into the board. Okay, that was part A. All right, so part B, it says, what was the time required for the electron to move from A to B? Okay. Well, remember one thing, right? So I want to find basically the time when particle is moving with some constant speed and covers certain distance. All right, so what is the distance it's covering? Well, it's from A to B. That's the, half the, circumference, right? What is the distance, half the circumference? Is just pi r. So remember, so what we had here is the speed is equals to distance pi r divided by time. Well, then I use this to solve for the time then, which is distance over the speed. That means pi r divided by the speed. Well, pi times 0.05 meters, that's for the pi times radius, divided by speed, which is 1.41 times 10 to the 6 meters per second. So meters cancel out, second goes up, and what I get here is 1.11 times 10 to the negative 7 seconds, which is roughly 110, 111 nanoseconds. So obviously it's moving really fast, so it covers that time in no time. So like it's very, very quick. All right, so that was part B. Okay, here's one more example. And this one, we have a proton moving in a 65 centimeter radius circular orbit that is perpendicular to a uniform magnetic field of a magnitude 0.75 Tesla. Right, so that means we're given that it's a proton. That means I'm given charge, okay? I'm given now its mass. If you remember, then it's 1.67 times 10 to the negative 27 kilograms. And I'm given that magnetic field is 0.75 Tesla. And it's, I don't have the direction, but I know one thing, it's perpendicular to the direction of the motion, okay? So then radius is then 0.65 meters. Those are the things I'm given, right? So charge, mass, magnetic field, radius. I want to find radial orbital period for this motion, okay? Well, remember, right? So I derived that equation for you. So period is equals to 2 pi times m divided by q times b, right? Again, you can start with the centripetal force equals qvb, then derive it, all the way to this equation. But once you derive that equation, right, you get this. And then from there, it's 2 pi times the mass, 1.67 times 10 to the negative 27 kilograms, divided by charge, 1.6 times 10 to the negative 19 coulomb, times B, which is 0.75 Tesla. So you can see, right, period, there's no radius in this case. Well, we get roughly 87 nanoseconds for the time, for the period. That means it takes 87 nanoseconds to go around one time. All right, so part B says, then what is the speed of that proton? Well, now I can, solve for the speed, because I know speed is equals to distance over time, which is 2 pi r over the period. Distance over, if the distance is circumference, then time is the period. Then 2 pi times 0.65 meters divided by 87, roughly, times 10 to the negative 9 seconds. So if I do that, I get 4.67 times 10 to the 7 meter per second. Or let's say round this to 4.7 times 10 to the 7 meters per second. So that's the speed. And the last one, it says, what is the kinetic energy of the proton? Well, kinetic energy is, remember, 1/2 mass times speed squared, right? So again, I put the mass, I put the speed, right? Remember, here's the mass, here's the speed I calculated. Well, what I get here is this, 1.87 times 10 to the negative 12 joules. But generally, when it's proton or electron, we represent energy in terms of electron volt, which is an energy unit. So I convert that where 1.6 times 10 to the negative 19 joules is defined as 1 electron volt. And that's going to give me 11 mega electron volt as the unit, as the value for the kinetic energy in that unit of electron volts. All right. Okay. So few other things that I have here that I want to talk about is, if you kind of talk about in more general sense, right? So technically there's always going to be like not only magnetic force, also electric force. So let's say this is being the net force. So then net force on a particle where there could be electric or magnetic phenomenon is then vector sum of the electric force and then magnetic force. Because it's always, relatively simple to create an experiment where the particle basically has magnetic and electric forces acting on it, okay? And that, let's say, think like this. Here's a some kind of region where there's a magnetic field, right? So when then here's a particle, let's say moving with some velocity. Remember, this is magnetic field in, right? So doing this, you can see that since velocity is down, negative j hat, magnetic field is negative k hat. When you do the cross product or use the right-hand rule, you can see there's a magnetic force in that direction. But one thing I can also do here, I can put plates here. I can make this plate as positive and this one is negative. So what do I get when there's a positive and negative plates like that? I get electric field. An electric field will be in this direction. And if there's a particle positive moving in this region where there's an electric field to the left, where then there's also going to be electric force to the left in the direction of electric field. So now you can see, right, it's being pulled to the right by electric force, magnetic force is being pushed, or you can think like to the left by electric force. And which one is stronger, then, it's going to dominate, right? So let's say if magnetic force is stronger, it's going to go like that. If electric force is stronger, it's going to deflect like that. If both the same, they're going to cancel and particle is going to go straight down, right? So this is known as a Lorentz force, okay, which is the vector sum of the electric force and magnetic force, okay? So you can always look at it in terms of that. Remember, this is, Q times E, this is QVB, let's say, right? And you can add them together if they're on the same axis. So for example, here you can see both of them are horizontal. I could have added them together. So QE minus QVB, right? QE minus QVB. And if they're the same in magnitude, you can see, right? That's why you get 0. There is no net force. You can go straight down. Okay. And that's kind of what we get here. That's the idea of what we call a velocity selector device. Okay, so you can see that there's a magnetic field into the board, and particle now, let's say, okay, so here's the direction of the force, and a little bit different from what I have. So let's say particle is moving up, and while we're using a right-hand rule, magnetic field right now is to the left. Then you put plates, and magnetic electric force is to the right, exactly opposite of what I had. I should have, I forgot in which direction, but in any case, so exactly the same scenario. Now, the idea here is this magnetic force and magnetic field, magnetic force and electric force are both on the same axis, both of them, so we can see from sort of like horizontal, right? That means when I'm doing the vector sum to find the net force, to see what happens here, I'm basically looking at this. So QE to the right minus QVB to the left. Minus means it's, it's negative, right? So, and what I have here then, so this QE minus QVB, that's what I get as my net force. Well, the idea here is that if they are equal in magnitude but opposite direction, then you get 0 as a net force. 0 net force means that, you cancel Q from both sides, then you get E equals V times B. And this just represents how electric field and magnetic field are related, right? And you use that then to find the speed, E over B. Okay, so that's what we have over there. That means you can calculate what should be the speed for that particle if you have an electric field and magnetic field. Because if I have the strength of the electric field and strength of the magnetic field, I can calculate what should be the speed of that particle so it goes in a straight line without being deflected. Because, for example, right, you can see in this, in tug of war, if electric force is stronger, it's going to be deflecting like that. If magnetic force is stronger, it's going to be deflected like that. If they're equal to one another, they cancel and goes a straight line. And we can do what we can do. We can select which particles go through that, let's say, the velocity selector device and with, let's say, specific speed. So that's why we choose particles that have that designated speed in order to go through that, device. All right, so because one thing we can do here is if I use that, if I have the magnitude of electric field and magnetic field, which is, relatively simple to get from this, experimentally, right? Then I can figure out if the particle moving through this, there's this, let's say, first chamber. So here's the first one, right? If it's going through here, what will be the speed as it enters the second chamber? Okay, the speed is equals to E over B, that's it. If now I have that, the speed, that means what I can do here is I have a second chamber over here, which has only magnetic field, which means that when there's a particle entering here with this velocity, which I select, right, and I know I can calculate that, then I know from that point on is only magnetic force acting on it because there's only magnetic field. And those magnetic fields are different. So this is, you can think like a different magnetic field. But what I have here is this. Well, let's say even if it's the same, in this region too, right, there's only magnetic field. That means as soon as it enters, it's going to be deflected by the magnetic force because only magnetic force is there. And it's going to go, you can see, right, see the semicircular, path, trajectory, because force of, magnetic field always acting as a centripetal force and pointing in the direction of the center. So it's going to make it go like this. Okay. And then one of the things we can do here is we can see where it, hits the plate. This is the plate over there, measure the radius and use that to figure out the relationship of all of those things. All right. So this device is known as a mass spectrometer because once I get that, remember this equation that I have where mv squared over r equals qvb, right? Once I cancel that, you can see that I take this mass, I take this q, find their ratio, m over q, and this is equals to r v naught over v, okay? And this is what was used by J.J. Thomson, because J.J. Thomson did this experiment in 1890 something, almost like 1900, like 1897, 98, where he was trying to find mass of the electron over the charge of the electron. Let's say this was an electron, because up to that point, mass of the electron was unknown. Charge of the electron was unknown. That means 120 years ago, those values, right? Mass and electric charge was unknown. So, but what he was able to do here, he was able to find this ratio. So technically what he did, he found E over M ratio. But if you can see, right, if you find the reciprocal, so this is just V over RB, okay? So E over M ratio is just that, okay? So you can then, in terms of take that and find this ratio. What you find whatever this ratio is. So let's say this ratio E over M is some number. And then later, if you have any type of experiment where you can find either charge or the mass, you can come back and find the other one. Because you have the ratio, all you need is to find one of them and you can find the other, okay? So that's why, he did this experiment. He was able to find this E over M ratio, and then later on find individual charge and mass of the electrons. All right, so here you go. So J.J. Thomson in 1897 was able to measure this ratio E over M for the electron. Okay, and that's the basis for any type of cathode ray tubes, which is if you remember those big big TVs, right? We used to have those CRT TVs that they all use this type of device, which is it's known as an electron accelerator. So they would accelerate the electrons and deflect them and then generate the screen, right? Okay, so the magnitude of the two fields are first adjusted to produce this undeflected beam for that device, right? And then the magnetic field is turned off. The electric field produces a measurable beam at deflection that is recorded on the fluorescent screen. From the size of the deflection and the measurable values E and B, the charge to mass ratio can be determined. So that's basically the experimental, setup for that. Okay. And one other thing I can have here is I talked about the cyclotron frequency. Remember, cyclotron is a device that accelerates charged particles to a very high speed. Okay, so it's kind of like you put something and it starts accelerating because there's some kind of AC circuits. We might come back to cyclotron later on when we kind of go over the AC circuits a little bit. But the idea here is this, there's this kinetic energy, 1/2 mv squared. Then what we do here, we replace some of those things, right? Let's say the speed and thing like that with this equation from the previous, equation for that. And we're gonna end up with this, where kinetic energy can be calculated by charge square, magnetic field square, radius square over 2 times the mass, okay? And we're able to do that. We don't really go too much of the cyclotron here, but that's something that can be used as a tool to, for the scientists to analyze some of those relationships. All right, so this concludes part 1. So I'm going to post this and later on post part 2 for this chapter, which will be then on looking at current, current carrying wires generating magnetic field. And we're going to be a relationship of those type of things and Ampere's law, and look at the, some of those Biot-Savart law and Ampere's law, right? Look at the more detailed calculation of those things.